Morning is Professor Dieter Lüst, and we'll talk about the Gravitino and the Swampland. I would like to ask people, in order to keep strictly the program, because there are so many speakers, do not interrupt the speaker with short questions or something that will be can be later asked, and also the people from the remote attendees, I would like to ask them to wait until the 5 minutes before the end of the talk. They could ask. Okay, thank you.
Yeah, thank you, Magnolis, for introducing me. And of course, I like to express really my great pleasure and gratitude to be here in Corfu after 2 years. It's really very nice to be back. So thank you, George, and all the other organizers for putting this Humboldt Collect together. I also maybe like to say that many of you here have good connections to the Humboldt foundations, and indeed I also like to thank the Humboldt Foundation for the support for this meeting. So you have a connection as a Humboldt Fellow or as a Humboldt awardee, example Kostas Bahas and Renata Kalos and Andre Linde were Humboldt awardees in Munich, and I'm very glad that they are participating. So many thanks to the Humboldt Foundation. I think they're doing really a very important. They have a very important role in German science, and I was also for several years, not anymore, in the Humboldt committee, and I know very well how difficult it is also often to choose people, because there are also so many excellent candidates. So what I want to talk today is about the Gravitino and the Swampland. And in fact, this is work joined with Niccolò Scribiori, actually another Humboldt fellow who will join our institute in October. So right now, Markus Calisi, and also some earlier work with Eran Palti and Kumun Wafa. Let me start with a remark about particle physics. I think this is also important that as we are doing quantum gravity or string theory, we should not lose the contact to our friends in particle physics and even to the experimentalists. But unfortunately, as we know, it looks like that at the moment supersymmetry, at least low energy supersymmetry, is not favored by experiments. So I think the experimental bounds, at least roughly, that the SUSY partners should be all heavier than 1 TeV, and I show you this plot here about some neutral, about some neutralino masses. I do not discuss these plots anymore, but there is no sign of supersymmetry, at least from the experimental point of view. So maybe then one should also ask, is there any fundamental reason, not against supersymmetry at all, but at least against low energy supersymmetry? And combining supersymmetry with gravity, as you know, we have local supersymmetry, supergravity. There the spin 2 graviton, the massless spin 2 graviton of Einstein gravity has a unique superpartner, the spin 3½ Gravitino, and almost in the same way as the graviton is a very fundamental particle, at least in supergravity, the Gravitino is also a very fundamental particle. And there's a very simple relation between the scale of supersymmetry breaking in SUSY square, the Planck mass, and the Gravitino mass. So if you have the experimental bound that the SUSY scale is in the order of the TeV scale or heavier, then one gets also a bound on the Gravitino mass. It has to be heavier than a few millievolt. And I think this is a strict bound for the experiment, which cannot be avoided or has to be respected in any fundamental, in any model which also comes from fundamental physics. So we can pose the question also the same in equivalent way, namely, is there any fundamental reason against the light gravitino? And that's basically the question I want to ask, or I want to ask and address in the talk. So what we like to ask in particular is if we can get any information about the scalar supersymmetry or the mass of the gravitino from basic properties of quantum gravity. In fact, similar questions can be also asked about the mass of the graviton or higher spin particles. Also, other people are working on the subject, about the cosmological constant, and we even considered the so-called Swampland constraints about the number of space-time dimensions. In fact, we like to address this question now is in the context of the Swampland program, which became kind of popular during the recent years. And the Swampland program is addressing the question which infrared consistent quantum field theories cannot be embedded into a UV complete quantum gravity theory. So this picture, I think you have even seen here in the workshop, if you were also participating at the previous workshop. It is a sketch about the swampland and the landscape. So suppose we have a theory of quantum gravity or string theory in the UV, and we have to go down to the infrared. Then the so-called string landscape is opening up. These are the all the effective field theories for infrared, which can be lifted to quantum gravity. But this landscape is surrounded by a large swampland, and those are all quantum field theories which apparently are completely consistent. For example, they are normally free and fulfill all the other criteria one has to impose on a quantum field theory, but apparently there's an obstruction to derive them from quantum gravity. So this is a swampland idea, and there are several swampland conjectures now. These conjectures basically also all address the borderline between the landscape and the swampland. So because we have to know where we enter the swampland or the landscape, it's basically the same question. Some of them are rigorous, some of them are less rigorous, some of them are useful in phenomenology, some of them are less useful. One can say they are often motivated from general black hole properties, and during the recent years there was a lot of work to test them in string theory. So I think it's also fair to say that most of the tests, or perhaps even exclusively, are done within the context of string theory, and there's even the question of the so-called string lamppost principle, whether at the end all quantum gravities have a string theory origin. Here we, as I said before, we like to talk about the gravitino. So this is what we call the gravitino mass conjecture. I hope to show you that it is well motivated and also partly tested in string theory. And following my introduction, I think it is also useful in phenomenology. So before we come to this, I want to give you a very brief look back into the history of the landscape in the swampland. I think in 1985, everybody was kind of being very enthusiastic and optimistic. That were the days of the first string theory revolution, and it was said by many relevant people in the field that string theory is unique, and indeed it presumably is still unique. But it was also transferred. So this statement was also transferred to the real world, to the infrared in our modern language. And at that time, basically, the swampland did not exist, and the landscape was just one point. Everybody was thinking, for example, the heterotic string compactified to 4 dimensions leads to a unique answer in 4 dimensions. This turned out not to be the case, and soon after, one can say, was the beginning of the landscape. It started with several observations. I think it's fair to say that when we and other people like Costas also in the room, and Kawai, Levin and Hai, trying to construct string theories directly in 4 dimensions by lattices and also fermions. It was obvious, it was realized that there are many more possibilities. And for example, in our paper, we were quoting already this relatively big number by looking of possibilities to construct 4D string theories by so-called covariant lattices. Of course, these were not really yet, these 4-dimensional string constructions were not really discrete string vacua in the more modern sense. And I think this began with the appearance of the so-called flux vacua, and but also about with the appearance of KKLT. And here a typical number was 10 to 500. I think this is an estimate by Mike Douglas about the number of flux vacua. And sometimes this is also called the starting point of the landscape. This number increased. For example, there's a very nice paper by Taylor and Wang trying to estimate the number of F-theory vacua, and they get a much bigger number. So as you can see from this picture, the landscape proliferated enormously. So it grew and grew and grew, and I don't know whether it's still growing. I will give an argument against. So here it seemed also that almost everything goes, and that also gave to the picture of the multiverse and the anthropic principle, which also other communities got interested in, like in philosophy. So there was a lot of debate, also controversial debate about this picture. Now with the Swampland idea, it seems to me at least that the Swampland constraints are rather, some of them are rather, they are interesting and they are rather severe. And it looks like that the landscape is apparently shrinking again. And there's, I think, good evidence due to many interesting observations, also in the context of flux vacua, due to constraints like tadpole constraints and so on, that the landscape is shrinking again. And okay, we don't know yet, but perhaps at the end we are again arriving at the point where almost nothing goes. But this is still open, and of course we do not know. Presumably we will end somewhere in between. And of course you might also argue if we do not have 10 to 500 vacua, but only 10 to 490, you don't really care. I mean, but I think this is a question which will be has to be decided in the future, and I think there's a very interesting development. So after these more general remarks, I showed you the outline of my talk. I review some of the Swampland conjectures. Then I come to one particular one, the so-called ADS distance conjecture. This is then already related to the Gravitino mass conjecture, and if I have time, I will also discuss some phenomenological consequences. So let me come to a few so-called Swampland conjectures, and the first one is the no global symmetry conjecture. I think this is one of the oldest, and I think also one of the best motivated or even proven Swampland conjecture. It says that a theory with a finite number of states coupled to gravity cannot have exact global symmetries. The emphasis is also on a finite number of states. And for example, it tells you also that the global baryon number cannot be exactly preserved in quantum gravity. So we can now go one step further and try to gauge the global symmetry, introducing a Billian coupling constant. I call it GU1. And then one can refine the statement a little bit that the global limit of sending this coupling constant G to 0, so going to weak coupling, is apparently obstructed in quantum gravity. Yes. Then the next step is the so-called weak gravity conjecture. So we couple Maxwell gauge theory to gravity with the standard version, with the standard Lagrangian. And then we have the electric version of the weak gravity conjecture. And it is saying that there always exists a particle in the theory with mass m and charge q that is satisfying this relation. So the mass must be always smaller than the electric charge times the coupling constant, always measured in Planck units. So it tells you basically that the gravitational force should be always the weakest force in town when you compare it with, for example, with electromagnetism. And there's also a magnetic version. If you not consider the electrically charged particles, but the magnetic monopoles, and there's a natural cutoff in the theory given by the size of the magnetic monopole, which also sets the cutoff of the effective field theory. And the magnetic version is that the cutoff of the effective field theory is bounded again by the electromagnetic coupling constant. So lambda has to be smaller than G measured in Planck units. And this will be important. This relation will be important for our considerations in the following. And in particular, it now introduces in the effective field theory a so-called Swampland scale, which we denote by lambda, capital lambda Swampland. And if lambda Swampland is lower than any characteristic energy scale of the effective field theory, then the entire effective field theory belongs to the Swampland. So there's a nice picture. We have the effective field theory, lambda swamp with the cutoff scale. So below this scale, the effective field theory is valid. And what is happening very often that above the cutoff scale, there's an infinite tower of states, and it is the presence of this infinitely many states that is invalidating the effective field theory description above lambda Swampland. So then the next step is, I think, in this logical series of conjectures is the Swampland distance conjecture. And it's saying that at large distances delta, so large distance delta in the parameter space of string vacuum, there must be an infinite tower of states with some particular mass scale little m, and at least in the asymptotic regions of the moduli space, the mass scale m is related to the distance in this exponential way. So if the distance is large, this mass scale m becomes smaller and smaller, and basically the effective field theory breaks down at this mass scale small m, and you see lambda Swampland becomes much smaller than the Planck length when capital delta becomes very large. In a little bit more technical terms, capital delta determines the so-called geodesic distance in the so-called moduli 5-parameter space of backgrounds. So delta is a function of the scalar fields of the moduli scalar fields. For example, if you study a string compactification, and then you have also an effective action for the scalar fields, and possibly also with a potential. And for example, if you choose the scalar fields to have canonical kinetic energy, then the distance is basically proportional to the scalar field vacuum expectation value times the so far undetermined fall of parameter lambda, which also then would appear here in this formula. So this particular constant lambda is the model dependent. It has to be determined in any particular quantum gravity or string theory realization. So in string compactifications, the Swampland distance conjecture is often due to the higher dimensional nature of the theory, and it basically means that there's a particular scale, namely the well-known Kaluza-Klein scale, where a new dimension is opening up, and then this mass scale little m can be identified with a Kaluza-Klein mass scale. So it is given by 1 over the radius, the scale or the volume of the internal space. The distance is then nothing else than the logarithm of the radius, and the relevant tower of states which become light in the infinite radius limit are nothing else than the Kaluza-Klein particles with masses n over r. And I think the picture is completely consistent and nice, because these Kaluza-Klein particles, they're also charged with respect to the Kaluza-Klein being engaged symmetry, and their electric charges also go like 1 over r. So if you put things together, you get, at least in this case, a completely consistent picture. But as I said before, there are in general more parameters, and like other gauge couplings, masses, they all depend on the scalar fields phi. And in particular, we like to know what is happening in certain limits or infinite distance limits, where some of these couplings, G, or some of the masses become very slow, very small. And we want to see whether these limits are again obstructed in quantum gravity in the sense that they are related to lowering the cutoff of the theory, and if they are accompanied by a tower of light states. All right. So now I want to switch to two concrete examples of these distance conjectures. The first one is the so-called ADS distance conjecture, which we have considered with Eran Palti and Kumun Wafa more than 2 years ago. So we are considering here ADS d vacuum. D is the dimension of the ADS space in quantum gravity with a varying negative cosmological constant lambda cc. And now the ADS distance conjecture is claiming that there exists an infinite tower of states with mass scale little m, as I again denoted, that behaves, which scales with a certain power of the cosmological constant. So there's a parameter alpha here, and the distance conjecture is also claiming that this parameter alpha is constrained from below. It is bigger than 1/2. So you see, if lambda also if the ADS coupling, if the ADS cosmological constant, which is negative, becomes small, the mass scale also goes to 0, and then the claim is that there should be again a tower of states which emerges. So basically the effective field theory again breaks down the limit where the ADS coupling constant becomes small, which also means basically that the ADS quantum gravity cannot exist alone as a consistent background. Typically, again, for small cosmological constants, some other compact dimensions will opening up, and this has also some interesting implications for possible dual CFT descriptions. The strong version of the ADS distance conjecture puts a stronger bound, namely this is a case where alpha is 1/2, and one can show that this is basically saturated for supersymmetric ADS vacuum. So again, we have the same picture. There's an infinite tower, and you can test this. I mean, in many known and perhaps even more complicated situations like string theory, M theory on ADS 5 times S5. And here it is again, the tower is again realized by the Kaluza-Klein states, which come from the compact which come from the compact part of the entire 10-dimensional geometry. Now I want to go a step further. I think the ADS distance conjecture is originally thought to apply for anti-de Sitter spaces with a negative cosmological constant, but we can also try to see what is going to happen for backgrounds with a positive cosmological constant. I do not want to enter the debate now here whether they are possible or not in string theory, but we can just assume that they are there at least, and we assume that the ADC is also valid for de Sitter spaces. But in this case, you would get really a very strong prediction, namely that in the standard cosmological scenario, the ADC would lead to the prediction that there should be a tower of states of the mass of the order of 10 to minus 120 times the Planck mass, just because of the known fact that the known positive cosmological constant in the universe is so tiny. Of course, again, there's this unknown parameter alpha here, so alpha could be very tiny, then the prediction would be so dramatic. But in any case, if this would also hold for de Sitter spaces, if they exist, one would have to ask what could be this tower of states, and how could it escape observations. There are some interesting papers on the subject. I think people were speculating this that this could have something to do with the dark matter problem, but I think it would, for me, at least, to say the least, is a very strong prediction which comes here, and therefore I want to see whether we can refine the ADC for cases where we have broken supersymmetry and also for vacuum with positive cosmological constant. That is now where we come eventually to the Gravitino mass conjecture. As I said to you before, this is a paper with Nicolo and Marco Scalisi, Nicolo Cubio, Marco Zul, both from the Max Planck Institute. And one day later, there was a very similar paper by the Spanish group. So it appeared a day later on the archive. They called it not the Gravitino mass conjecture, but I think the Gravitino, the infinite distance conjecture of the Gravitino. And somehow we were a bit lucky because I think 2 days ago, before we submitted our paper, we still had basically the same title as theirs, and then changed our title. So everything went fine. If you are very careful, you can see in a footnote, even there we were not careful. We somehow the old title of our paper is there. In any case, the idea is completely the same. And here the conjecture is again there's a mass scale little m, which is related to the Gravitino mass in this particular way. Again, there's a model-dependent parameter n, which we should remember, and basically the cutoff of the theory or the mass scale m scaled with the Gravitino mass in this way, where n should be positive. And indeed, if this were true for small Gravitino masses, the mass scale little m would also go to 0, and then the effective field theory description would break down. Of course, we can compare this immediately with the previous ADS conjecture, and there we know that m3½ square is given by minus lambda over 3, and in this case, the ADC and the GMC stands for Gravitino mass conjecture, are completely equivalent to each other. Note also that the case where m3½ is 0 is a bit special and needs some extra treatment. It's not necessarily continuously related to finite Gravitino masses, and this is also often the case for these conjectures. The endpoint in moduli space needs some extra treatment, and we are basically always considering the asymptotic region where you approach the boundary of the moduli space. But in case of broken supersymmetry, one always has that the Gravitino mass square has to be strictly larger than minus lambda over 3. And in this case, the ADC and the GMC indeed lead to different conclusions. In particular, the GMC now allows for a situation where we send the cosmological constant maybe positive or negative to 0, but still keeping m3½ finite. And perhaps from the phenomenological point of view, this is a bit more favored situation by reasons which I explained before. So this limit would not predict a tower of light states, whereas the ADC alone would always predict a light tower of states. Okay, and this has also possibly to do with this problem of scale and mass separation, which I do not touch here in this talk. So while the GMC could be true, there are at least two simple situations where we can provide further evidence for it. The first scenario is that the Gravitino mass is again related to extra dimensions, and then it follows from the normal distance conjecture. But there's also a very interesting complementary scenario in many string compactification which originate from extended supersymmetries. The Gravitino mass is related to a U1 gauge coupling, which means that the Gravitino itself is charged under U1 gauge coupling. And then the GMC follows from the magnetic gravity conjecture, and I also mentioned this briefly later on. How much time do I have on this?
It's 14 minutes.
To me?
14 minutes.
14 minutes. 14 minutes.
14. 1-4.
Yeah, I think we are sure about it. Because we started at 9:40, George.
14.
Good.
1-4. 40.
So let me go through this very briefly. If I were able to switch the slide. So let me come to the case of extra dimensions. Then the effective action, the NP1 effective action, besides the Gravitino contains a certain number of states, namely scalar fields phi, the modular parameters of the compactification, their couplings are determined by the scalar potential K and the superpotential W, and the kinetic term of the scalars, which eventually determines the distance in parameter space, is given by a particular nonlinear sigma model. Supersymmetry is broken if either the F terms or D terms are 0. Here I list only the form of the F terms. I am rather quick here because I assume that many of you know these formulas. So for non-vanishing F terms, which are related to the Kähler covariant derivative of the superpotential, supersymmetry is broken. And then one gets these famous relations here for the Gravitino mass square. It's given by e to the k times w square. And also the cosmological constant, namely the scalar potential, can be computed. It has a gravitational contribution, which is negative, namely -3 times the Gravitino mass square, and the F term contribution, which is always strictly positive. And from this, we also get this bound that M3 half square is bigger than minus lambda over 3. So we can now study the behavior of these quantities of the Gravitino mass and of the cosmological constant as function of the scalar fields in the moduli space. And then typically one gets that the Kaluza-Klein mass scale is given by 1 over the volume in 4 dimensions for compactifications to 4 dimensions with a power 2 over 3. You can also estimate the Kähler potential. It is given by the log of the volume times alpha, possibly plus some extra contribution, and also the superpotential in the minimum after stabilization of the moduli scales with the volume in a particular way. And putting these together and comparing the Gravitino mass with the KK mass scale, you can derive now this parameter n, which determines the power law of the Gravitino mass in terms of the Kaluza-Klein scale. So you can take your favorite string compactification models, determine these 2 parameters alpha and beta, which determine the Kähler potential and the superpotential, and then you get this parameter n. So you can do this in many instances, for example, in KKLT, n is 1 over 3, but there are also some important log corrections which appear for Scherk-Schwarz models. N is 4 over 3. There's also the famous anti-brane uplift, which leads us to the zitter. And again, you can compute n. It is 1 over 3. So all these models basically positively test the Gravitino conjecture. Of course, there could be several details, but typically the Gravitino conjecture is satisfied in these scenarios. I also mentioned the case where the Gravitino is charged under U1 gauge symmetry. This happens, for example, in generically in n equals 2 scenarios. Here the Gravitino and the graviphoton have another superpartner in the extended supergraviton multiplied. It is the so-called graviphoton. It is a U1 gauge boson, and using the very nice formalism of gauged supergravities with a prepotential and moments. At the end, you see that the Gravitino mass is very often generically proportional to the gauge coupling constant of the Gravitino to this extra U1 gauge symmetry. And again, now we have a very good argument because sending G3 half to 0 is obstructed because it would lead to a global symmetry, and therefore also the limit of M3 half is obstructed and shouldn't be possible in quantum gravity. Okay, so in the last 5 minutes, I discussed briefly some applications. Let me first be a little bit more precise about the quantum gravity cutoff. I was so far basically saying that the quantum gravity cutoff is related to this mass scale little m of the distance conjecture, but one can refine this a little bit because the scale where gravity becomes strongly coupled is in fact the so-called species scale, which is given by m Planck over square root of n, where n is the number of light species in a particular effective field theory. But this can be immediately translated to the distance conjecture. Yes, so if the species are built by the tower of states we were discussing before, then n, the number of species, is basically given by lambda quantum gravity divided by m. And then you get this relation between the cutoff scale of quantum gravity, where gravity becomes strongly coupled in the Planck mass. It scales in this particular way. And again, this parameter n, which appeared in the Gravitino mass conjecture, appears here in this relation. If you express now everything in terms of the Gravitino mass. So we have m3 half over m Planck with a power n over 3. And I think this is also an interesting relation. It basically tells you that the Gravitino mass is smaller than the cutoff scale of quantum gravity only if n is smaller than 3. And in fact, there are scenarios where n is bigger than 3, which would mean that for n bigger than 3, there's no effective field theory of supersymmetry breaking. So this we would not even call effective supersymmetric quantum field theories. You can also use the bound for the charge Gravitino. It would lead you to a similar inequality, and again, it can only be true or meaningful, I would say. It could be true also for other ends, but it only makes sense for n smaller than 3. So finally, I want to apply this to inflation because in the past there was already a lot of discussion whether inflation can be realized in a meaningful way in theories which have low energy supersymmetry. And in general, as it was, I think, also mentioned by other speakers in the conference, clearly the Hubble scale of inflation in an effective field theory must be smaller than this cutoff lambda quantum gravity in order to make an effective field theory description of inflation meaningful. So we can now translate this into a bound of the Gravitino mass using the previous formulas. It's a rather easy exercise. And then you get an interesting relation that the Gravitino mass is bounded from below by h in this particular way. So in Planck units, the Gravitino mass has to be bigger than h with a power 3 over n. And the case of n equals 3 is again interesting. That is basically the turnover point where the Gravitino mass is of the same order as the cutoff scale. But at this turnover point, it happens to be that m3 half is typically generically bigger than the Hubble scale. That was already observed by Karasch and Linde several years ago. And this really causes a tension between inflation, I think, and low energy supersymmetry, because in this case, supersymmetry, the typical supersymmetric particle, namely the Gravitino, is heavier, is above the scale of inflation. So the breaking must, in this case, must be higher than the scale of inflation. We can finally compare this with CMB data and the scalar to tensor ratio. Then H is given by this famous quantity R in this way, which determines the scalar to tensor ratio. And then we can translate this again into a bound for m3 half. And since we know that currently R must be smaller than 0.06, the next CMB experiments try to reach R of the orders of 10 to minus 3. So basically now we can test, using this relation, one can test even mass scales for supersymmetry breaking or for the Gravitino, which are much higher than the millievolts, which I have mentioned before. In this case, we would enter the region of several hundred GeV for the Gravitino mass. Okay. So again, plotted this for several values of n. So R, so m3 half is a function of R, you can see in this plot. And yeah, basically that's what I wanted to say. So it's a very quick outlook. Let me summarize. There are various Swampland conjectures motivated from strings and branes. Many of them are related or hinting at deeper common origin. I discussed two specific Swampland conjectures. The Ante de Sitter distance conjecture, which is setting the cutoff of the theory in terms of lambda ADS, and the Gravitino mass conjecture, which is setting the cutoff of the theory in terms of m3 half. And indeed, most likely there's also another parametric relation between m3 half and lambda, which puts these two conjectures even closer together. We saw that we have strong constraints from inflation on m3 half, basically saying that the scale of SUSY breaking is of the order or higher than the scale of inflation. And this plot at the end of my talk shows these various scales which have a nature starting with the cosmological constant, the actual weak mass scale, the scale of inflation, M3 half, the Swampland mass scale, lambda Swampland, a bit higher, the species mass scale, lambda QG, and finally the Planck length. So in this way, somehow we at least at the moment, we can order our various mass scale which appear in quantum gravity or in the effective supergravity theory, and blending in again the picture of the landscape or the swampland. Basically, maybe just a take-home message from my lecture here is that low-energy supersymmetry apparently belongs to the swampland. Of course, this is open for discussion, and I'd like to thank you with that.
Thank you, Dieter, for your very interesting talk. And I would like to ask if there are any questions first from the present people in this room, and then from the remotely connected. Yes, please.
Thanks for this nice talk. I have a question about the ADS distance conjecture. So you showed masses, but you could have also shown anomalous scaling dimensions of the dual CFT operators. Now, what does it imply for the CFT, your conjecture? Does it imply a condensing tower of operators, or simply an infinite tower, but which doesn't condense to a classical limit?
Okay, yeah, thanks for this nice question, Kostas. I think it firstly maybe tells you that in many of those CFT duals there should be a mass gap, because otherwise the spectrum becomes gapless, or as you say, many of the conformal dimension of the operators become lighter and smaller and smaller. So I think this is basically would be the generic feature which translates from the bulk distance conjecture into the CFT. And then I think there are a few groups who started already this behavior. And let me say that 1 week or 2 weeks ago, there was a very interesting paper by Aharoni and Palti, who translated the not this distance conjecture, but they are related, as I explained. However, they translated the weak gravity conjecture. They formulated the weak gravity conjecture in terms of CFT data, and they got a very interesting result. It has to do with certain convexity properties of conformal dimensions of charge operators in the CFT. And I think indeed it looks like that there are equivalent conjectures which you can also now formulate in CFT. And in CFT, they have their own right, but and they're also not completely understood. And seemingly they have a very nice counterpart in the ADS or in the gravity bulk.
Okay, thank you. If there is any other question? Yes, please.
Thank you. So the question is, how small the number of AQI has to be for you to be like, okay, we can go over them one by one and see whether there is something there. So what is the smallest possible number for that?
Right. So I mean, clearly I cannot give you a conclusive answer, whether it's 10 to 500 or only 1,000. I mean, if it were 1,000 or 1 million or 1 billion, I think it would be extremely easy to scan over them with modern computer techniques, also with machine learning and these things. And people start to do this. So there is already a lot of activity in this so-called machine learning community applied to string vacua. People look at flux vacua, their distributions. They look at other constraints coming from constraining fluxes by the tadpole and so on. So this is done, or at least partly done. But of course, if the number still keeps as high as 10 to, I showed you this extremely high number of Taylor and Wang for F-theory, one has to look at particular corners or invent very smart algorithms, I think, to get a useful result. But I think we are not at the end, and perhaps at the end of the day, we will be able to constrain considerably the number of vacuum. But as I was also saying, if it's 10 to 1,000 or 10 to 300, in practical terms, I think this will not make a huge difference. I'm not sure whether it should be 10 or even 1, because I think this is, or maybe it's nice, but I think this will not happen because we know already that there are many consistent string vacuum, so also in lower dimensions. So I do not expect only 10 vacuum.
Okay, so can you take if there is any from the remote people that are asking for just one question only? You can hear. So then, thank you very much again. So the next speaker is Professor Kim.
Hello.
Is remote. Yes.
We can't hear you, Professor.
Hello?
Oh, yes.
Hello?
Try again.
Yes, I try to share my.
We can see it.
Can you see?
Yes.
Okay.
Okay, Professor Kim, thank you very much for your participation. And Professor Kim will talk about the black hole information problem. Okay, thank you. Go ahead, please.
Thanks for the organizing committee for giving me chance for this talk, even as an online one. Since 2019, I am with the visitors to Corfu. I wanted to go there this year also, but because of Corona-19, I couldn't go. Usually, I start my talk with this cartoon. This CDM is WIMP or invisible action, or quintessential action, which I worked with Peter Niles and visible stuff. Where all this has information, dark energy, CDM, and atom has informations. So do black holes. Black holes affect all these three categories. This talk is a simple point on what you all already know. I just relate one known mathematical lemma to the black hole. Example for black hole is simply charged black hole. Well, we know that black hole entropy was pointed out by Bekenstein. He pointed out black hole and thermodynamics have similarities. A large black hole always increases mass by absorbing nearby masses. Thermodynamic system loses more information as time goes on. So for black holes, combining two same mass black holes, the surface area always increases. In thermodynamics, and surface area always decreases. In thermodynamic, entropy increases. So he related these two ideas, two observed facts. And for black hole radius, the horizon radius 2gm, and the surface area calculated from this horizon radius is about Planck mass square times mass square. It is roughly this one. So from this relation, black hole entropy is in terms of dimensionless surface area, or in terms of information, it is proportional to some m square, irreducible mass m square over Planck mass square. So this is the information we have. For ultralight action, well, I mentioned about ultralight action as some CDM component. And in this case, mass ranges is allowed between 10 to minus 33 electron volt to 10 to minus 3 electron volt. But some of these regions are excluded by observed structure formation data. So this region, in this figure, the lavender part is the allowed regions for ULA. If our visible universe is a black hole, then the information carried by this visible universe is about 10 to the 122, 123. Well, recently, Coriano and Frampton commented about probably our whole visible universe is a black hole. In this case, this number of informations I just showed, how can it be provided by some particles, etc. So in this paper, it was commented that if it is ULA mass of order of 10 to minus 32 electron volt, then the information number 10 to the 122 may be provided by ULAs. So in which case, whole universe, visible universe is a black hole. In this paper, it also commented that WIMP cannot be for this providing all the needed information. The reason this very line mass ULA can provide this information is mass is so small, so you need very many number of ULAs to fill the whole universe for this to become black hole. But I am not paying attention to this phenomenal one, but I look for a logical possibility. Here, I present just an idea. It may be right or wrong. So for information, we know that a massless particle has two polarizations. Massive particle has three polarizations, but all this number of information can be digitized. We can express information in the numbers. In this case, if irreducible mass is there, the possible digitation of mass is expressed in terms of dimensionless number, exponential dimensionless number. So for black hole radius, the Bekenstein's irreducible mass less than 10 to the minus 5 gram distinguishes which information is more for particle case or mass case. For the mass, if irreducible mass is greater than 10 to the minus 5 gram, information of mass is more important. So for these large black holes, we always talk about information in terms of mass, irrespective of individual particles. So in our discussion, we consider black holes with the mass greater than 10 to the minus 5 gram. Well, suppose that we punctuate the whole, so there is a black hole, the whole of diameter L on the black hole surface as in the left-hand side figure. So there's the gray area is showing the black hole surface. If there is an even number of these punctuated holes, then we can always connect these two punctures, and in the end, there nothing remains. If there are odd number of punctures, then after removing all even numbers, there remains one puncture. This cannot be removed. So through this puncture, maybe we can see inside the black hole. In this case, if we consider puncture, waves with wavelengths greater than L cannot come out from the black hole inside. So, but in my talk, we are not considering all these particles. We are just considering this puncture. However small it is, we consider this puncture. Maybe the smallest size L is Planck length. So as shown in this figure, left-hand side figure, if we consider around the black hole, we consider test surface of this figure, then from one remaining puncture, if the flux line comes out, it can come out and it has to end somewhere. It should end only on the surface of the black hole, as shown in this figure, because this is a trapped flux lines cannot end at some point in the above area. It can land only on the surface of the black hole. So in a sense, if this is possible, puncture can connect to inside information. All this information is recorded on the surface of the black hole. If surface of the, we know the information of the, on the surface of the black hole, we know information inside the black hole. So this is the Bekenstein formula. This is the M. And I just introduce you, remind you the spariness lemma, because I wanted to relate this spariness lemma to this one puncture of the black hole. Actually, triangle is topologically the same as a disk. So if disk, rubber disk covers the surface of the black hole, then maybe also triangle can cover the surface of the black hole. Anyway, triangle rubber cloth can cover the surface of space, so we consider triangle to cover the black hole. If there is a puncture, the boundary of the puncture, I show the boundary of puncture as arrow lines. And in this, in the lattice gauge theory, people consider calculate the placket, and if you integrate over this boundary, you obtain placket, which is a gauge field square, integrate over the surface. But in this, if this circle or square or triangle, this inside this one, how? So I consider in this case this triangle, because triangle is the simplest two-dimensional geometry. So if the reason I consider triangle is the simplest one, and in this triangle, the vertex is numbered as PQR. So if it is 1, 2, 3, it is the simplest case. Where inside this triangle, inside it can be, if we consider PQR, then inside is like some PQR dependent area. So which I consider is F mu nu A. A is in a sense showing the adjoint representation of some group. This point is numbered by PQR. So depending on PQR, the quantity to be integrated inside is given by this adjoint representation. Spariness lemma is there is an odd number of white triangles in this figure. Well, what is white? In this case, if PQR is 1, 2, 3, 1, 2, 3 is numbered as, for example, in SU3 gauge theory, I consider red, green, blue. If I consider PQR as red, green, blue, inside depend on one number of triangle PQR, one number of PQR is used. That determines the adjoint represent A inside the area. Actually, this Spariness lemma was proven in this homepage, Math Fun Fact of Harvard University to undergraduate students. So the proof is very simple. And I consider SU3, which is numbered by 1, 2, 3 to match colors of SU3. So this is a PQR. So if this triangle is divided by smaller triangles, as shown in this case, the bottom line 1, 2, and the side lines 1, 3 or 2, 3. The side lines 1, 3 is numbered by 1 and 3 only. Side line 2, 3 is numbered 2 and 3. Side line 1, 2 is numbered 1 and 2 only. Then along this bottom line AB, there is a 1, 2. You can count the smaller 1, 2 lines, small lines 1, 2, 2, 1, 1, 2. Actually, there are 3 small 1, 2 lines, small 1, 2 lines. Long 1, 2 lines is the whole baseline, but there are only 3 small 1, 2 lines. And then this on the bottom line, there is always, in this case, odd number of small 1, 2 lines. So that is what Spariness lemma tells. On the bottom line, there's only odd number of AB lines. So this, but in the counting of the AB in the whole triangle, if you find out small 1, 2, you give 1 for that line. If you find 1, 2 in the internal line, because there are 2 ways. One time you goes up, one time you goes down. So square 2 for internal AB. All others, 1, 3, 2, 3, etc., square 0 for all others. Then the number of small AB line is only at the bottom segment, which I showed you before. That's the total number of small AB line is odd. In this, as this example shows. Now, we can count the number of triangles. So this is what I explained before. There are 3 1, 2 lines in the bottom line. For triangles, square 1 for every triangle 1, 2, 3. If it is 1, 2, 3, square 1. If for every triangle with AAB or ABB, square 2, all others square 0, then the total square of number of triangles is the same as the number of smaller AB lines. Because we showed the number of smaller AB lines is odd, the total number of small triangles is actually odd. That's the number of small. ABC is actually triangle with AB, 1, 2, 3. If triangle, end point of triangle is 1, 2, 3, then inside is actually SU3 invariant quantity, F mu nu A. This inside one is F mu. Well, I show this in terms of colors. If I color 1 as red, 2 as blue, 3 as green, then this left-hand side shows these colorings of this SU3. So the previous case, I colored all these small triangles. Then some parts are yellow, some parts are green, some parts are lavender, red, etc. And there's only one triangle. In this case, there's only one triangle with white. White means this is one the end point 1 to 3. That means through this part there is a gauge invariant one, SU3 invariant one. So with this triangle, if I cover the black hole, there is one triangle from which gauge invariant quantity can come out. So flux lines with the if we go through any other lines, it breaks SU3 gauge invariance, as this color triangle shows. Only through this one triangle, gauge invariant flux can come out. And as I showed in the beginning with this punctures, through this one small triangle, flux lines of inside information come out and it can land on the surface of the black hole. If this area, one small area of Planck length square of order counts one information, then this black hole surface of 10 to the 122 information is given by the number of small triangles on the surface. Actually, anyway, so this spareness lemma, which is very simple, and it is very simple to prove, is that if we consider black hole, and if we consider some gauge field inside the black hole, then always there must be one puncture. There must be one puncture through which gauge invariant flux can come out. That's what I wanted to show. So this white triangle, gauge invariant flux can come out. So I showed that there's an inevitable one puncture, and the space lemma guarantees it. I showed with the SU3 color example. Thank you for your attention for this short talk. It's too short?
Professor Kim, thank you for your talk. Are there any questions? Are there any questions from the people who are online? No. If so, thank you again. Professor Sagnotti following. Thank you. Around, but he's not
George, do you hear me? George?
Yes. Augusto?
Yes, do you hear me, George?
Yeah, I hear you, yeah.
The video
Can
is
you
stopped.
stop?
The video is stopped. You have to authorize it, and you should also authorize the share screen because I don't think I, no, now I can, now I can. Okay, now I
Okay.
can.
We are waiting for you. Yeah, fine.
Yeah, now I'm sharing the screen. I can do it now. Just one moment. Should be able to go full screen. Do you see it? Do you see it, George?
Okay, we see you. Okay, Augusto, this is Emmanuel Floratos. Hello.
Oh, hi. Nice to hear you, let's say.
Okay, Professor Sagnotti will talk about string stability and stability issues with broken supersymmetry.
Okay.
Okay, Augusto, go on, please.
Okay, very good. I'll keep track of the time. Thank you very much. And let me get going right away. This is the title. You've seen it. It's related to this work with mostly with Jihad Murad. And so let me start from the motivation, if you want. This is well known to all of you. There is this famous hexagon of dualities in 10 dimensions, some of which are well-established perturbative features of 10-dimensional strings, and some of which are very brilliant conjectures that are largely due to Edward Witten. But they are largely due also to lessons drawn from the low-energy supergravity. So the question is, what happens if you add to the picture broken supersymmetry? Because this hexagon concerns 5 10-dimensional string theories which are supersymmetric, and their links with the 11-dimensional supergravity of Kremer, Julia, and Scherk. So the next slide tries to address this point. So the first thing to say is that if you allow for broken supersymmetry, the diagram widens. And actually, you can go from any point of this diagram to any other via orbifold or orientifold conjecture. This is not always stressed because, for instance, the link between type 2A and type 2B is usually rightfully associated to toroidal compactifications and T-duality, but as a matter of fact, by orbifold or orientifold projections, you can go through all this diagram. And typically what you find is that the addition of the option of having broken supersymmetry brings along the emergence of tachyons. But there are 3 notable exceptions to this rule. One of them is a heterotic model. Here I spelled out more clearly what it is, and here it's simply indicated as HE2. If you want, it's obtained as a peculiar orbifold of the E8 cross E8 heterotic string. Then here, there is another model, which is tachyon-free and non-supersymmetric, and it's obtained from this 0B string, which is a tachyonic orbifold, of the type 2B string. And the third model is a peculiar orientifold of type 2B, which is different from the supersymmetric type 1. It differs from that in the gauge group, which moves, if you want, from SO32 to USP32, leaving in unchanged the fermionic matter content, which of course has to rearrange in representations of the new gauge group, with the end result that there is a singlet, and the singlet signals the fact that the model has a nonlinear realization of supersymmetry. Now, when all these things take place, as you have seen from the picture, you can enlarge all your perturbative dualities if you want. We're playing around a little bit with string consistency rules. What we are missing in this wider set is an understanding of the possible non-perturbative links. Another new datum that emerges is that the low-energy effective field theory has a distinct sign of the breaking of supersymmetry. So the distinctive sign of the breaking of supersymmetry is the emergence of what we call usually the tadpole potential. It's a runaway potential for the dilaton field. So let me pause briefly on one of the 3 models where supersymmetry is non-linearly realized. This has a peculiar origin, if you want, this phenomenon. If you want, the standard supersymmetric SO32 string is a soup, if you want, that you get filling the vacuum with extended objects in this brane picture. There are denying branes and orientifold branes which can absorb both the tension and the charge of these branes. The result is a vacuum with no residual charge, as it should be, but also with no residual tension. and this vacuum is supersymmetric. There is a minor change that one can make because there is another BPS object called O9 plus orientifold, which has positive tension and positive charge. If you put this object in the vacuum, then there is a problem because in order to cancel the charge of this object, which you must do, you must use anti-branes. The charge cancels, but the tension adds, and the added tension reflects itself in the emergence of this potential. What happens at the level of states is very interesting. If you want naively, the states of one type are lifted with respect to the others. And in this respect, you can say that the string scale is the scale of supersymmetry breaking. So if you want this kind of model that in some sense I keep in mind in many respects, although the others have similar behavior, the other two have similar behavior, is a model where the breaking of supersymmetry is realized at very high scales, at the string scale. Now, the problem is that we don't really have a well-defined bona fide way of analyzing this problem. The reason is that what we know about string theory in general is a double perturbative expansion in terms of alpha prime times typical curvatures and in terms of the string coupling. What we can do is just take into account this potential and try to go as far as we can with a word of caution on any region where either of these two quantities becomes large. And let me anticipate that we will be rather successful in maintaining the second quantity small, but not so successful in maintaining the other one small. So we have really no way to find solutions where this one is small, but many different realizations of cases in which the second one is. Now, let me start then by discussing these vacuum solutions. The first type of situation that was analyzed, if you want, in general, if you want, has to do with cosmology. Actually, the original work that started all this is always the work of Dudas and Murad that I will quote extensively for the vacua. But basically, we took a different look with Emiliano and Kitazawa in 2010, and we realized that there is something to learn from the systematics of how the model changes as this coefficient gamma varies. The other term that I put here in blue brackets is, if you want, a phenomenological addition that I will justify shortly. But the basic lesson is the following, that if this coefficient lambda is less than a critical value, say that in 10 dimension is 3/2, and this in canonical normalization for the scalar, then there is a striking phenomenon that occurs starting from this value when the value of gamma overcomes and actually reaches and then overcomes 3/2. In principle, as you can imagine, if this potential were a flat horizontal line, the scalar can emerge from the initial singularity from the left and from the right without any difference. But when you tilt this potential, making it into a steep exponential one, remarkably, when the exponent becomes precisely the exponent that pertains to the orientifold model, 2 out of 3 in 10 dimensions that I was mentioning to you before, then the scalar becomes what we call the climbing scalar. The climbing idea is just a pictorial representation of the fact that there is no solution where the scalar emerges from the initial singularity from large values. What the scalar can do is increase, reach a maximum. So it's like an object that climbs on this exponential and then come back. From string theory, from the string theory perspective, this makes a big difference because we've solved the strong coupling problem. Half of this series, if you want, is under control. What can you learn from this kind of situation? What you can learn from this kind of situation is that if you start, this could be, of course, with an addition of a phenomenological second term, a model for the beginning of inflation from a fast roll to, from a fast roll state, which is, if you want, natural for the early universe, to the slow roll condition that characterizes inflation problem. And this has variable effects on the power spectrum of scalar perturbations and also the one of tensor perturbations, with peaks that depend a little bit, which are not universal in this region, but with the genuine universal effect of cutting off the power. So in principle, this could be a model, or if you want, a rationale for the low quadrupole in the CMB. I will be short here, and people know that there are many ifs related to cosmic variance and the like, but I just wanted to mention this fact. The second case is what I will be mostly concerned with, is what I will call the Dudas-Murad vacuum, and it's really the paradigm of all this type of investigations. Now you see, I wrote down this the solution, because if you want, the basic datum is that when you have this exponential potential, flat space is not anymore a vacuum for the theory, as it is normally for the 10-dimensional supersymmetric strings. However, thanks to the presence of the dilaton, if you want, the tadpole effects can pile up, and this results in internal space. So if you want, in a 9-dimensional vacuum, Minkowski-like vacuum, Minkowski vacuum actually, where there is a finite value for the Planck mass, so that gravity remains effective, the cumulative effects on the dilaton create an internal interval of finite length, of length proportional to 1 over square root of t, where the t is the tension. And the finite length, you can see it immediately from here, because if you integrate the square root of this quantity from 0 to infinity, you get a finite result. So you have an interval of finite length, and you have at one end of this interval the dilaton, which goes to weak coupling, phi goes to minus infinity, but at the other end, the dilaton goes to plus infinity. There are many questions. So in this case, differently from what I showed you in the fermionic context, we have strong coupling regions for the dilaton at the right end, and there is a curvature singularity at the origin. So the question is, how much can we believe this? And the second is what happens if you consider perturbations of this vacuum. Is it stable or not? Because in the presence of supersymmetry, stability is guaranteed, but when you break supersymmetry, there's nothing like that. So we have to investigate it explicitly. The third type of vacuum that we investigated, and actually it was investigated in one special case by Gupser and Mitre before us, is what happens if you try to look for very symmetrical solutions. Very symmetrical solutions meaning ADS cross S type vacuum. And now there are broken supersymmetry counterparts of the familiar ADS cross S vacua, which are sustained by fluxes of the forms that are typical in these theories. And to cut the long story short, these vacua have everything that you can possibly demand. They can be excluding regions of strong curvature, and they can be at weak coupling all the way. So this vacua would be, if you want, the ideal starting point. We know that the perturbative series can be completely under control. However, we recently investigated other types of vacua that are a bit more general than the Dudas-Murad vacuum originally, because they allow for the possibility of anisotropies, if you want. Or if you will, they consider they can describe compactifications to p+1 Minkowski spaces, and if the internal coordinates are taken to be periodic, cross tori times an internal direction, which can be an interval or finite or infinite length. If you want, roughly speaking, the presence of the interval eats up the effects of the tadpole, when the tadpole will be present, and the rest is essentially, in principle, something that one could replace with a compactification on a Ricci flat internal manifold. This is just the simplest case of that. So if you want, compared to the supersymmetric case, you use an interval to absorb the effects of the tadpole. You end up in Minkowski space. And actually, the simplest solutions of this type are obtained when there is neither a tadpole nor any flux. And these are Kastner-like solutions with, where the dilaton plays a role. And the general solution of this Einstein equations, in this case, is characterized by a pair of equations, a linear relation and a quadratic relation concerning the exponents alpha A, alpha C, and alpha phi that enter in the behavior of the two sets of spatial coordinates and the dilaton. Now, if you go and solve these equations, they define clearly an ellipse, and the ellipse can be parameterized by an angle. If you solve these equations, then you find an interesting, surprising little fact. that one of these equations involves precisely the coefficient gamma c, which in 10 dimensions would be 3/2, which characterize the tadpole exponent of orientifolds, which was not u a priori in this case, but you will see why this happens. More generally, one can analyze non-supersymmetric vacua for supersymmetric strings. Incidentally, the first type of vacua that I showed you here include for mu equals 0 flat space, but for mu different from 0, they all break supersymmetry. So if you want, mu can be characterized as the scale of supersymmetry breaking in this vacua. The second type of vacua involve a flux, a special type of flux which is symmetric. If you want an analogy, is the more sophisticated counterpart of the electric field that enters the Reissner-Nostrom black hole, for example. And an example of this vacua where the flux involves the self-dual 5-form field strength of type 2b is shown here. The reason why I showed you these equations is because close to the r equals 0, where the form becomes singular, these equations, the sinh function becomes a linear function, and this background becomes supersymmetric. So in other words, this background approaches a supersymmetric background, which has a Killing vector, preserves half of the original supersymmetry of 10 dimensions at one end. Again, let me stress these are still vacua with no tadpole, so vacua of the supersymmetric strings. But they involve an internal interval at one end of which the vacuum approaches a supersymmetric solution. At the other end, the vacuum approaches one of these Castle-like solutions with very specific alpha A, alpha C, and alpha phi. You can verify that the constraints are satisfied. What is more surprising is that a pattern of this sort, whereby at one end, actually at both ends in this case, in the Dudas-Murad vacuum, even though the tadpole has a crucial effect in driving the phenomenon of compactification, the asymptotic behavior of the vacuum becomes similar to the asymptotic behavior of vacua with no tadpole whatsoever. Actually, to be really precise, this peculiar behavior occurs for gamma equal gamma c for the orientifold value of gamma and for lower values of gamma, which, if you want, resonates with the idea that this nonlinear realization of supersymmetry in the brane supersymmetry breaking context in the USP32 model is a soft phenomenon. On the other hand, if one considers values of gamma larger than gamma c, which pertain the SO16 because SO16 heterotic string, this mild behavior is not possible anymore. And the asymptotic behavior remembers, in some cases or other, when I put different from 0, the presence of the tadpole. So in other words, to reiterate, the asymptotic value is described by a Castle-like solution where the exponent satisfies those constraints, which know nothing about the tadpole itself. But this is true for gamma less than or equal the value, the critical value that concerns orientifold model. The same critical value that was imposing the climbing phenomenon on the gamma equal 3/2 case. If you want to say it differently, the critical value behaves like the hypercritical ones in cosmology and like the undercritical ones in spatial solutions. Now there is a more general, and this is what I wanted to stress here, precisely the presence of asymptotic behaviors that remember the presence of the tadpole. So they are harder. The other thing that one can study, generalizing this type of setup by simply analytic continuation of the previous results, is a bunch of cosmologies which are anisotropic. If you want, cosmologies which contain two sets of dimensions, the x's, and the radial variable now has become this cosmic parametric time, not to be confused with cosmic time, which would be defined by integral e to the b dt. And the second set of coordinates that we have the possibility of considering compactified on an internal torus, or if you want in more general terms on a Ricci flat internal manifold. Now the basic information that one can gather from this is the following, that for gamma less than or equal gamma c, asymptotically all these cosmologies become isotropic. So in other words, there could be some coordinates that contract initially, others that expand, and they become isotropic. And now this cosmology that I show you is a clumping scalar cosmology. So the scalar, the dilaton has an upper bound, and so the string coupling, and it's weakly coupled at the initial singularity. This is another example for gamma larger than gamma c, where the situation changes again. Here you can have a different option. So to say it explicitly for the SO16 cross SO16 model, or I should say it for completeness, that type of tadpole with gamma equal 5/2 or counterparts in lower dimensions always presents itself in the presence of Scherk-Schwarz breaking. So this type of considerations also apply to Scherk-Schwarz compactifications that create an effect on the vacuum like this at one reporter. So in this case, you can have some dimension that dynamically compactify and some dimension that continues to expand forever. If you want, it's a dynamical model of compactification. Now, what is the general setup? The general setup of this type of solutions, which depend on a single coordinate, let it be a radial coordinate, an internal spatial coordinates of time, is rather rich, because they can describe a number of properties of vacuum that I will try to finish to illustrate, but also black holes, of course, spherical black holes. And now the point is that you have these three functions. Clearly, B is a redundant function because you can see that any reparameterization of R can just simply change B. There is a preferred gauge choice or coordinate choice, if you will, which we call the harmonic gauge, where B is this linear combination of A and C. We call it the harmonic gauge because the left-hand side of this equation becomes simply a second derivative. There's no nonlinear terms on the left-hand side, but there are many nonlinear terms, of course, on the right-hand side. And so if you want this system are reminiscent of Toda systems, but they are not integrable in general. Now, there is another peculiar property of these systems because I'm not showing them in full generality. These fluxes are the analog of the contribution of the electric field in a Rice-Nordstrom setup, but there are also counterparts of constant electric fields. And then, of course, there are the magnetic duals. So the equations can be more complicated than this. And then there is a discrete symmetry that relates the H fluxes to the small h ones. Now, in general, one can analyze this system in terms of three variables. Actually, it's not completely general because there are some cases in which you have to use two of these and the dilaton. But let me be almost completely general, just for simplicity. And now the idea is to use as basic fields some quantities that are, if you want, suggested by the exponents. Now the system takes an ether form. In particular, you can notice that there is a big simplification in the dynamics when gamma is that peculiar value gamma c. Because the system CU has a trivial dynamics. It's a linear function. And now the remaining system becomes triangular. Actually, there is a special value of B that I will illustrate shortly, where even the second coefficient vanishes. And B depends on the, if you want, on the order of on P, if you want, on P and the dimension of space-time. There's a special case in which also this vanishes, and then the system becomes exactly integrable in elementary terms. And there's a lot of interesting information. Let me illustrate one case when this happens. It's a solution with H7 flux and gamma C critical tadpole potential. Now there is an instructive set of exact solutions. There are actually three families. What I will concentrate on now is a family where this quantity x1 is negative, so I wrote it as minus absolute value x1. Now, to cut the long story short, what happens is, in this case, the cumulative tadpole effect that led to strong coupling in the Dudas-Murat setting cannot take place. Or if you want to say it better, it takes place in the wrong direction. So the presence of the flux makes space-time stop at the origin. And the cumulative effects would take place as the variable r tends to minus infinity. But in these solutions, it's impossible. As a result, you can have solutions where you have a singularity at the origin, where, however, the vacuum approaches a supersymmetric solution. And then you have a mild behavior at infinity, where the string coupling can also be finite to zero. There remains a very interesting fact that the internal direction remains finite. So you have compactifications of this type. Now, let me turn to, in the last part of this talk, to the issue of stability. Now, the first models that we analyzed from this point of view are the quote unquote obvious solutions. Of course, we know that other people have analyzed this type of issues from other viewpoints, and the results that we obtained is resonant with these various types of information that have been gathered from ADS CFT or otherwise on ADS vacua. But we found it interesting to see it firsthand, if you want. And what happens is that in this paper with Ivano Basile in 2018, we analyzed the perturbations of this vacua. Now, this is a complicated story because it's fraught with complications introduced by gauge symmetry, but it's partly simplified, the analysis in this case, because you are talking about ADS vacua. So to talk about perturbable stability or not, all you have to do is look at the mass operator, if you want, and check whether the eigenvalues of this mass operator for the various sets of modes satisfy or don't satisfy the Breitenlone-Friedman bounds. So if you want in flat space, negative values of M squared would signal instabilities. In ADS, negative values below a certain bound would have the same effect. And now what we found is that in the two models, the two compactifications that we had found, sustained by an if you want an electric three-form flux or the magnetic counterpart, there are instabilities. Now this diagram, I like it for pictorial reasons, that it has no quantitative value in absolute terms, but you see that the point that signals the actual values of certain parameters in the theory is very close to the stability region. So in principle, we are almost there. And actually, it's even possible to eliminate the perturbative instabilities by putting projections in the internal space. To tell you the full story, we succeeded in the heterotic case because it's enough to do a pairwise identification of antipodal points in S3, creating an internal non-orientable manifold. But we know from other studies of other people that non-perturbative instabilities show up in this context. But we didn't find any solution of this type for the orientifold. So the orientifold solution here is which is this one, by the way. The other one concerns the SO16 plus SO16 theory. The orientifold solution, we have not managed to make it stable. Then we turned let me turn to cosmology. There's another instance where we found an instability. And now, in the context of the Dudas-Murad model, if you want, or its cosmological counterpart. But now the instability is interesting. It's not a sickness, in our opinion. It's a very interesting phenomenon. What happens is that if you look at tensor perturbations, the scalar perturbations are okay. Now, what do we mean by the instability? We mean that we put a perturbation at the beginning and we follow it through the cosmological evolution. What happens is that scalar perturbations dump, and tensor perturbations do the same, typically, unless we focus on a very special sector with k equals 0. In the sector with k equals 0, there is a remarkable mild instability that essentially shows up while the scalar climbs up. And this instability, if you want, can be characterized as an instability of isotropy. So if you're not, in other words, if you take this kind of model indications seriously as potential lessons, it is possible that the lower dimensional space-time that we live in was the result of a chance, if you want, of an instability that let some directions overcome the others. And interesting, this result resonates with these papers. I'm not enough of an expert to establish the connection directly, but perhaps rather than answering a question, I can ask one to our colleagues, and maybe we can have a nice discussion on this point. So this is the second case. Now the stabilities start, and the first surprising result, we obtained it from the Dudas-Murad vacuum. The Dudas-Murad vacuum has this strong coupling, but there is an elegant way of addressing stability problems. Now, the potential instabilities in this case concern scalar perturbations. So you parameterize the scalar perturbations in a form that will resonate with many of you who have seen works on cosmology. And then you find an equation for scalar perturbations, which is complicated. So of course, it's a linear equation by construction, but it's complicated. And yet we can discuss very efficiently what happens to the spectrum of M squared. The trick is to recast the equation in a Schrödinger-like form, introducing one of these guys, the creation and annihilation operator pair, A and A dagger. And then you will find that the equation itself can be formulated in this way, that this eigenvalue M squared is determined by the spectrum of this operator, which with proper boundary conditions is a positive operator, or non-negative operator rather, sorry. And B, the addition of this potential is a manifestly positive quantity. So scalar perturbations are consistently stable in the Dudas-Murad setting. Now, the fact that the boundary conditions play a role led us to study boundary conditions in general for Fermi fields and for Bose fields, but I will skip this part of the talk because we are running late. The bottom line that I want to convey to you is that the conditions for the boundary condition that one should adopt have to do with this combination, square root of G times the radial times radial space-time, say portions of the energy momentum tensor, and the square root of minus G times radial internal. I always have this ABC type of vacuum. And then there are other conditions that have to do with the angular momentum generator in space-time. Now, to cut the story short, for fermions, you are led to higher dimensional counterparts of Neveu-Schwarz or Ramond sectors, Neveu-Schwarz ones associated to Scherk-Schwarz deformation, but I will skip this thing. And I want to end this discussion with the explicit analysis of a vacuum that already appeared in our discussion. This vacuum is a vacuum of type 2b, so no tadpole. Supersymmetry is broken by the presence of an internal flux. There is a finite internal interval. As R goes to 0, the background approaches a supersymmetric background. And as R goes to infinity, there is a finite length. So it's a compactification to lower dimensional Minkowski space of type 2b, if you will. Now, we want to study the perturbations of this vacuum to try to see whether it's benign like the Dudas-Murad vacuum. But the computation is much more complicated, and is much more complicated both technically and conceptually. The technical complication is that is related to the form, if you want, that is unfamiliar, but it's also conceptually more complicated for a reason that will become apparent shortly. To give you an idea of the complication, these are the self-dual conditions for the phi-form field strength that translate into some coupled differential equations for these various components after you decompose this form in terms of the symmetries of the residual four-dimensional space-time. This is a compactification to 4 dimensions, I should stress it.
Augusto, I'm
Yes?
sorry, I'd like to remind you that you have only 5 minutes left.
Yeah, no, I'm finishing. That's why I skipped the other part, because I'm about to finish the talk. I don't want to go beyond time. This is essentially my penultimate slide, so that I will not overflow. Now, when you do this type of compactifications, you have a phenomenon that already showed up in the ADS cross S vacuum. Now, in the ADS cross S vacuum, what happens is that the system was showing some instabilities which arose from the mixing of Kaluza-Klein modes with the mixing of Kaluza-Klein modes, if you want. Now here, the same type of phenomenon can occur, and it does occur. But there is a big difference. I'm sorry, they're ringing at the door here because I'm working at home, but I cannot answer clearly at this stage. So now this is the counterpart of what was being done in the ADS cross S case. Now in the ADS cross S case, all we have to do is look at the mass squared. Here we cannot do it because the compactive feature is more complicated. But what we can do is recast the problem in terms of a Schrödinger-like system. So this is the key, Schrödinger-like systems. If you recast the problem in terms of a Schrödinger-like system, then what happens, I'm sorry, I have to stop 1 minute because they are keeping to, I'll be back right away. Okay, sorry. This is the Schrödinger-like system. Now, what happens in the Schrödinger-like system? You see the diagonal elements are manifestly positive. The off-diagonal terms, however, can create a problem because if you think about the sigma-1 matrix, you will understand the pattern. What is our tool? When we have a Schrödinger-like system, we can pretend that we're doing quantum mechanics. So before we were doing this thing, if we pretend to be doing quantum mechanics, then looking at the lower bound of an m squared is equivalent to finding, if you want, an estimate for the ground state energy of the Schrödinger system. And we know that there is an extremely powerful method to do that, which is the variational method. It's the basis of all chemistry, if you want. So we do a variational test on the ground state, and what do we find? We find that there are instabilities, and then at some point the instabilities disappear, if you want, because the diagonal terms dominate here. And then what can we do? Are we lost like in ADS? Not at all. Because in this case, since you are ending up in Minkowski space, there is no correlation between the size of the internal space and your four-dimensional world. Therefore, all you need to do is squeeze a little bit the internal space, or if you want, put an upper bound on the radius of the internal torus, and then your first available mode will be this one, translated here, and you will have no instabilities. So in other words, with a bound on the internal size, which is completely compatible with being well below the string scale, you can eliminate the instabilities. This has to do with certain vector perturbations. But actually, the situation is even more complicated for scalar perturbations. And here there is a subtlety with which I will end up my presentation. The subtlety is the following, that the basic conceptual difficulty that we have in this system is that we don't know an a priori way of deducing the measure for perturbations that involve the self-dual phi form. The reason is that we don't have an action for that. The action is the key method for deducing a well-defined norm for the perturbations. For the self-dual phi form, we have no action, as you know, no conventional action. As a result, we have only indirect ways of deducing this proper form of the theory that gives you the right measure. In the previous case, we managed to do it because we ended up with a Schrödinger-like system, which is conventional. What happens for scalar perturbations is that you end up in a Schrödinger-like system where the matrix, if you want, the Hamiltonian is not Hermitian. The Hamiltonian has an anti-Hermitian part. And if you treat this Hamiltonian naively, you will see that you have a region where the eigenvalues are complex. But if the eigenvalues are complex for m squared, it means there are always unstable modes in M when you take the square root. Now, to cut the story short, what happens is that in this sector of the system, there is a parameter, which is essentially the flux of this phi form. And if the flux of the phi form is beyond a certain value, then the unstable modes disappear. So there is this peculiar fact that the system is not Hermitian, and so it is, you have different ways, so to speak, to formulate the variational problem, but all this, they all seem to converge to the same fact that for strong enough flux, there are no instabilities in this set. And this is the conclusion that I wanted to get to. I apologize for having to stop. So when we have analyzed many solutions that go from 10-dimensional or to 4-dimensional, or in general to Minkowski P+1 dimension, there are various types of solutions. No tension, no flux. These are Kastner-like, and they always have strong coupling. Tension and flux. What happens is that the flux puts a singularity, say at r equals 0, stops the growth of the coupling, and in this case, the string coupling can be bounded everywhere. Let me stress again that cases A and B have to do with solutions of the supersymmetric strings, no tadpole. If you turn on the tadpole, then what happens is that typically the tadpole closest space-time is into Das Morata. But this is accompanied by a real surprise that even though the tadpole does that, the asymptotics is tadpole free, at least for gamma less than or equal to gamma c. If you put tadpole and flux together, then there is something very interesting. That basically what can happen is that the growth associated to the tadpole of the string coupling can occur in the wrong direction, so to speak. And so the presence of the singularity induced by H can give a mild effect. In other words, you can have solutions of this type where the string coupling can be bounded everywhere. And you have a singularity, actually, so this is a bit too good what I wrote here. It's not quite correct. Cannot be bounded everywhere. It can be bounded on the region dominated by the tadpole. I should have corrected this. At the other end, what happens is that it becomes unbounded, but it approaches a supersymmetric behavior, so it should be milder somehow. All these results are also useful benchmarks to explore brain deformations by dealing with tadpoles. And we are starting to analyze that case. Now, just a leading final statement. Can we find solutions with bounds on GS? There are actually stable solutions that obtain if the potential is corrected by unbounded negative terms. So if you could imagine that the potential is corrected by non-perturbative means, giving an asymptotic behavior of this type, which not surprisingly is opposite to the tadpole terms that drive the climbing scalar in cosmology, then you can have bounds on the coupling. However, none of us, and also some previous work of Dudas and Condesco, succeeded in getting finite curvatures in this system. It is possible, although we don't know any concrete facts about it, that taking into account a series of curvature corrections would solve the problem. Anyway, my positive note is that there seems to be room for stable 4-dimensional Minkowski vacuum. And the reason is what I told you before, namely the fact that you can decouple the internal scale from space-time. Thank you very much.
Thank you, Augusto, for your interesting talk.
My apologies for having to stop.
No, it's okay. You are lucky. You are the last speaker before the coffee break.
There was a raised hand. Let's see.
There is no questions. So
No, I think there is a question. I see a raised hand.
I hope to see you soon. There is some.
Yes, I think there is a question.
I'm sorry.
Do you hear me?
Yes, Emil.
It's Emiliano.
Emilian, hi.
Yes, hi, Augusto. I had a question about the case in which you have no tadpole and flux.
Yes.
So this is presumably a kind of a spontaneous supersymmetry breaking.
Exactly.
Could you somehow see it more explicitly, like identifying the Agostino or looking at the Gravitino mass? What is the Gravitino mass, like that? It's
quite tricky. I skimmed all this stuff, but it's quite tricky because in the case that we looked at explicitly, we have actually a puzzle. And the puzzle is the following, that we know precisely how the fermionic spectrum would behave. And if you want, in rough terms, it is halved because of this Neves-Schwarz-Ramon type of story that I told you about. but we have an excess of bosonic modes. So we have a stable vacuum, barring that fact, but we have too many bosonic modes. Now it is possible that this vacuum is close, essentially these modes are lifted nearby, but there is a puzzle with that. Barring this fact, then you can see the Gostinos, because there is a pairing. If you want, since the spinos come from 10-dimensional type 2B, roughly speaking, the internal components of the Gravitino play the role of Gostinos, and that's only actually the way we understand what's happening. Because in this way, if the supersymmetry were broken, so if the Gravitino got mass in Minkowski space, then we would have no much trouble in accepting an excess of bosonic modes, because the fermionic modes would be up in the spectrum. So we do see them. They are essentially internal components of the Gravitino in this case.
Thank you. Thank you, Augusto.
Okay. I will stop sharing.
Now we have the coffee break. Until what time? Okay, so we come back at 12 o'clock.
Okay, thank you.